Hello, this is the Tepid Coder. Today I want to talk about common dependencies when you're using static libraries, not import libraries. And in particular, when I say common dependencies, I'm talking about your main project has a dependency, and one of your project's dependencies also shares that dependency. So like maybe you link in lib1, and lib1 requires lib2. Your main project also requires lib2. So when that happens, you could be getting all of the code from lib2 from lib1, but you could also just override the functions of lib1 and make it so that you're getting the functions from lib2 instead. And when you do that, and you link the project, it's going to use all of the features from lib2 that you linked directly, as long as you linked that first, because it'll resolve the symbols first. I talked about this in a previous video. Anyway, I specifically made this example to show that. So what I have is my test application here. It's going to require something called TC string that I made, which is like my own implementation of standard string, but way weaker and less featureful, just for an example. It also includes something called dependency.h. Now, dependency.h also requires TC string. However, they both are linking different versions of this TC string. But as I'm going to show you, there's no ABI break between the implementations as they're defined in the header and the actual implementation in the library files that I'll be creating and linking. So because there's no ABI break, it's going to work just fine, even though I'm using two different versions. Okay, so first off, let's talk about the versions of TC string that I made. My main, good version of TC string here is one that uses standard unique pointer and fills it full of a character array that's sized to the size of the string. I'm using standard copy to make it. So you can see right here, like if I assign it, it's going to say make a new unique pointer to a character array that has whatever the length of the string is, elements, plus 1 for the null terminator at the end. And then I just copy over whatever string was passed. That's all that's happening here. And in the structure, obviously, it doesn't need to do anything because it's going to be freed automatically by the unique pointer. Now, in my bad, with air quotes, implementation, what I'm doing is I'm using just stirdupe, which is a C function to duplicate a string, and I am freeing it with just a free function. So here's my destructor for this one. You can see I'm calling free, and when I'm actually assigning a string, it's going to use stirdupe. Okay, anyway, so what I have going on here in my test application is I'm calling a test function, and this test function wraps something I'm getting, create tstring. It's going to grab a pointer to one of these tstrings, and it's going to wrap it into a unique pointer. So when it goes out of scope, right here is the scope, right? When it gets here, this is going to be deleted, and it's going to call it a destructor, which is going to free the underlying TC string by calling delete whatever the TC string variable would be, right? TC string, you know. It's going to delete the internal TC string, TC pointer. And you might notice my keyboard's super quiet right now because I got that new membrane keyboard. It came a day early. Today's the 9th, so yay. You guys get to enjoy less clickety-clackety filled videos. Anyway, that's why I stuck this in the test function here. That way I can make it go out of scope, and then I could also print something afterwards, just so we can observe the behavior. Anyway, it's going to call a function that creates a string. I'm going to go over here. And this dependency file, right, it's going to be its own library. It just has this one function which depends upon TC string so that it can return a new TC string filled with whatever you passed it. Now keep in mind that this is grabbing the TC string version that has a unique pointer to a character array. Alright, and this test.cpp depends upon either just, in this case, the dependency, which has that built into it because they're both static libraries, or I can include the same version, or I can include a different version of the library to resolve the symbols and have them linked first. So first of all, let's run it and just show what it does. It's going to print whatever I set it with in the test function. So you can see it's working, testing 1, 2, 3. Okay. But that's just with only linking the dependency library, which includes in its file all of the code from TC strings. That's what it linked in, right? If I go to dependency right here, you can see it's loading in tcstring.lib. So it's that version of it. But But now what I want to show is, if I go over to my test.cpp file, I'm also going to link in the same version of the library. That'll work just fine. Let me see here. Oh, I need to fix the path. This is a project that I coded a while ago and didn't end up using, but then I thought I would repurpose it for use in this video, and I think it'll work out pretty well. Anyway, let's try and build that. Alright, so I'll run it, and you'll see it'll still work just fine. No issues, same thing happens. Obviously, I'm linking to the same library this one depends upon. The weirdness is going to be when I link to a different video, what the heck? Jeez. A different version that it depends on. Out tables, apparently. Outtakes, danger 1 / du / dll danger. It's going to take me some time to get used to typing on this keyboard, so I might be even worse at typing than usual. So now I'm going to link in the wrong version. And I'm going to run it, and you'll see it still works. Now, just to show that it actually is linking in the wrong version, for the first time on this channel, I think, in a video that I've released so far, I'm going to use a breakpoint. So we're going to debug with an actual debugger. I'm going to show what happens. So, what I can do here is if I look in my debug menu, I can step into something with F11, or I can step over it and skip an instruction with F10. I'm going to step into. Okay, so we moved into the function. Following the code, we're going to make a unique pointer, and it's going to make the unique pointer with create string from dependency library. Okay, now that's going to call TC string. And the interesting thing is, if you remember, I included the normal TC string implementation, not the bad one. However, let's step into it. Look, we're in bad TC string. And that's because I linked in this library right here, the bad one, in my test project. And it got linked in first, which means that the implementation in bad TC strings library is what resolved the symbols before the symbols in this one, which was linked against this library implementation, was able to resolve the symbols. So this got to it first. Everything was resolved here before it had a chance to resolve here. So that means I'm using a bad implementation. And you might think, well, geez, that's bad, right? Isn't this going to cause a problem? Well, no, and I'll show you why in a minute. Let's step through this a little bit. Okay, if I was initialized, we're going to assign it, call sturdy, call string length, return it. Okay, now this is going to return that bad implementation. Cool. That's fine because what we're linking against here is the bad implementation. They're going to be the same. Cool. Okay, returns the C string, it prints it to the console, it flushes the output. Okay, it's going to free it, which is fine because we allocated it with the bad one and we're freeing it with the bad one. Good. Okay, down here we say we finished and we return. And as you can see, it worked just fine. Now I'm not going to link in the wrong version this time, and we'll see what we get. I'm going to run it again. Now this time, we're going to follow it in. Oops, I don't want that. I want to go over here, F11. Okay, we're going to follow it. Now this time, let's see where it goes. It went to the normal TC string. See this? This is my good implementation, okay? This one uses a unique pointer. So let's keep going down. Okay, operator, make unique, copies it in with standard copy, returns a reference to the actual class itself, in case you want to chain. Okay, it's going to return this good instance. And this is pulling that version TC string from here because it's compiled into this in that lib file. Okay, we're going to print it out to the console. We use the C string function. We flush the console. We're back here. We're gonna, call the destructor, which does nothing really because it's got a unique pointer, and the unique pointer destructor gets called automatically, and that frees the unique pointer to a what do I say? It frees the character array that it allocated for us. Okay, so now return to the function. We say we finished. Return. We're done. And it's all well and good because it all uses the same version. And of course, if I compile the same version in both, that's also fine. To show that real quick, we'll step through it. Obviously, it's going to use the good version TC string because they're both compiling. We're linking against that one. Okay, everything works. Everything's fine. We're good. Cool. Okay, so let's talk a little bit about ABI-breaking changes. So essentially, what we have here, if we look at the header file, can I just jump right to that, TC string? We have a class that takes a unique pointer, and it has the length of the string that we're storing in the TC string class, okay? But this is private. This isn't exposed anywhere. We can't access that in test. We can't access that in dependency here. It's untouchable. It's a private member. But what we do have here in the TC string implementation is a constructor We have the constructor that takes specifically a const reference to a string. We have a copy constructor. We have a copy assignment operator overload. We have move constructor, move assignment operator overload. We have an assignment operator overload that specifically takes a string reference, and then we have the destructor and an accessor which lets us view the string. That's all we have exposed. And if you look at the bad TC string, you'll notice that the implementation, all the functions we have to access are exactly the same. The only thing that's changed is the private portion. The implementation, how we handle it in here, is really completely arbitrary. It doesn't matter because we didn't expose anything that has changed. Everything we've exposed works exactly the same way, has the same calling convention, expects the same sizes. So it doesn't really matter even if there is a mismatch between both of the implementations, because the way you interface with the implementation is consistent. So I really wanted to show that to talk about application binary interface breaking changes. That's what they mean when they say ABI breaking changes. It's like the actual interface, the way you act, the way you interface with the class, really. The way you use the class or object or function or whatever has changed. In this case, between both implementations, the good and bad one, the only thing that's changed is private. It's really implementation specifics that are completely arbitrary. So I hope this helps when you're thinking about linking projects, to know that the order of linking for libraries matters. And as long as there's no ABI breaking changes between the interface that you define in your headers, you can use whatever implementation you'd like. And it should work just fine. Obviously, that is still assuming that you're using the same compiler and the same version of the same compiler to build these libraries in the first place. So keep that in mind. But I think that's about going to do it for this one. If you have any suggestions on things I could add to this, if I need to, do any follow-up videos, definitely let me know. If there's something I got wrong, feel free to say something. And like, comment, and subscribe. I guess I'll catch you later. Have a good one.